Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our Finite Element Analysis and Design software, RFEM. The title for today's webinar is RFEM Webinar 1, Introduction to Analysis and Design. This is the first webinar of a three-part series, really geared towards our users who are not familiar with our software, starting with the basic introduction to the software and moving on to the more advanced features and finally ending with BIM integration, which will be part of that third webinar. My name is Amy Heilig. I'll be your presenter today. I'm the CEO of the U.S. office. I'm also technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Lucas Sunel will be your moderator. He's a product and customer support engineer located in Tiefenbach, Germany. If the control panel does seem to get in your way during this presentation when you logged into the GoToWebinar, you can show or hide that with the orange arrow up at the top. You also want to use this same control panel to ask questions throughout the webinar, as we always encourage you to do so. We'll do our best to get to all the questions, but if by chance we don't, I'll certainly send you a follow-up email afterwards. So real quick, to introduce who we are as a company and where we come from. We have been established for about 30 years now. Our headquarters are located in Tiefenbach, Germany. And in July of 2015, we opened up our Philadelphia, Pennsylvania office. This is really to be close to our existing clientele in the US and Canada, as well as to really emerge into those two markets as we had the existing standards in the software for both Canadian design and US design for our different materials. We also have additional offices in Germany, the Czech Republic, Poland, France, and Italy. And we're a company of about 200 employees. And the benefit of this is that these 200 employees are dedicated to only our structural analysis software. This is in contrast to a lot of other corporations and bigger companies that maybe have more people, but they have a lot of other products. So in turn, I think a lot of the structural analysis and design software takes a back seat in terms of development and addressing issues. So we really take that as an advantage at our company. We also have over 25,000 users in 71 countries all over the world. As far as the content for today's webinar, today I just want to give you a basic overview of RFEM and the add-on modules for those of you who are not familiar with the software at all. Then we'll take a look at a multi-material structure in RFEM, and here's where we'll be doing all of our modeling, our loading, taking a look at load combinations, and running a full analysis of this structure. Then we'll move into our add-on modules, and in particular, RF-STEEL AISC, where we'll be doing a steel member design per the AISC 360 standard. And in a similar manner, we will launch the RF Concrete add-on module, where we'll do concrete member design per the ACI 318. Lastly, we'll take a look at all of our results, whether that's in RFEM or these add-on modules in a little bit more detail, as well as the printout report options, as I think this is one of the stronger features in our software as well. So to quickly explain RFEM and the add-on module concept, RFEM is our main program. This is the Finite Element Analysis software. This is where we'll be doing all of our modeling for the structure for most of our materials, including sections from the different standards such as the AISC, the ADM, the CSA code. We can also integrate with BIM software such as Tekla, Revit, AutoCAD. And we'll be applying all of our loading to the structure as well, whether that's manual loading or we have a handful of load generators such as wind loads and snow loads per the ASCE 7. We can apply our load combinations, again, whether that's manually or according to the different standards, ASCE 7, the NBCC standards. And we run a full analysis in RFEM. This is where we can get things like deflections, internal forces, support reactions, and then we can also take all those results, put them in the printout report as well. Now, over on the right-hand side is just a very short list of some of the add-on modules that we have. You can see here that we have many different materials that we can involve the specific standards with. So the minute that you need a code check or design per that standard, such as the AISC or the CSA code, that will require an add-on module. Now, this is also in addition to maybe a little bit more advanced analysis, such as time history or response spectrum analysis. Stability, you can see, is listed down at the bottom. This is to get our buckling modes of our structure as well as the critical buckling load factors. Some of the materials that we have according to design include steel, concrete, timber, aluminum. We also have cross-laminated timber and glass in the program as well. So I just want to preface, today we're doing a very basic overview. I have done individual webinars that specifically target each one of these add-on modules that will go into much more detail than what we can possibly do today. So I always want to encourage everyone to go to our YouTube channel. You can just Google YouTube Dlubal and then search by keywords such as these to view those previously recorded webinars. And you'll hear me reference those throughout this webinar today as well. So with that said, we can jump into the program. So when I launch RFEM, the first thing that's going to pop up here is my general data dialog box. And what we need to do is to first give it a name. We'll just give this one name of webinar 10. Now the type of model you'll notice is a 3D. That's probably typically what you'll be in, but you do have the option to switch back to a 2D model if you'd like. And you can always establish this 2D model after the fact as well by going back into this general data dialog box to switch that to 2D. The orientation of the global z-axis, that by default is set to upward for the United States install. That's typically what we work with here. And under this details, we'll want to make sure that our local z-axis is set to downward. This is more so important for concrete design. Otherwise, it really doesn't matter in the program, but I always suggest if you have the global z-axis upward to set this as downward for our local member axis. Over here, we have the Create Combinations Automatically checked on. So when this is checked on, this is telling the program to automatically create these load combinations according to a specific standard that I select here in my dropdown. And this is where you can see that we have the ASCE 7 load combinations, IBC, we have the Canadian standard, as well as Eurocode and several other international standards. When I have this checked off, then I can manually create those load combinations. They won't be automatically created for me according to the specific standard. The template model down here is important because I think it's a very beneficial option. For me, I have this US template, and this just has the grid settings set up the way that I like, maybe my units. Perhaps I have some certain materials and cross sections that I use quite often. Well, once I'm in RFEM, I can always go to File, Save as Template, and then that template will be available in this drop-down here. This is great for companies who maybe do a lot of similar structures and all start off with the basic type structure to begin with. Well, you can model that basic structure and pull that up in your template model every time and then make further changes. So now we're ready to jump into the program. So when we first open up the model here, we have our graphics view located in the center of the screen. So as we begin to draw elements within the model, this is where they will begin to appear. Down at the bottom, we have all of our tables. A lot of engineers prefer to work with the tables, and you can certainly build an entire structure within these tables as well. What is great about the tables is that we have a nice button here for export and import table directly to and from Microsoft Excel. So you can copy and paste, but realistically this is a little bit more user-friendly. For example, we can export this table for our nodes to get the basic layout with all of the correct columns. We can input our data in Microsoft Excel, maybe sort some different ways, and then we can import directly from Excel according to the active workbook and worksheet that maybe we're in the background. A few other options that we have for modeling are, of course, all of our little tools up here, which we'll be using quite often today. We have our drop-down box up here. For example, we have all of the add-on modules listed according to the different categories, such as steel, concrete, dynamics. We also have the Project Navigator, and the Project Navigator is just another option to input your data. We will also view our results in the Project Navigator. So this first tab down here called Data, this would be all of our input data, and here is our long list of add-on modules here. So you can understand that we serve our customers the add-on module concept because we really want to create a software that's cater to you and your needs, rather than, hey, we need to charge you a very expensive software and you get all of these add-on modules regardless if you're going to use them or not. For example, you can see all of the different international steel codes that we have here that probably most of the time users aren't going to be utilizing this. So, as I mentioned, a very long add-on module list. The display tab really controls everything that we're viewing graphically here, including our results after we run an analysis, as well as the input data. Our views tab, it looks pretty empty right now, but as we begin to generate our structure, this will allow you as a user to create maybe user-defined views, to view certain materials and sections quickly, rather than having to highlight and select them graphically. Down at the bottom is some features that may look familiar. This is maybe something that you'd find in AutoCAD, such as object snap settings. If I right-click on this to open up my object snap settings, you'll see here the different checkboxes that we have for snapping to lines, to members, to surfaces. You'll see several are turned on by default, such as perpendicular, tangent. We can create different partition points along those lines. So very useful in terms of the AutoCAD-like capabilities within the software. And this is for the reason sometimes I tell users you're almost better off just starting modeling in our program rather than importing in a DXF file, because it's easier that way, because of all these different tools that we have. But with that said, you can import DXF files too. For example, under the background layers tab is where we can import in this DXF. And what's nice about the different background layers is I can put multiple layers in here. So maybe I have a different layout for every level of a multi-level story building. Well, I can go ahead and import in that DXF file at multiple elevations. The line grids option. If I create a new line grid here, you'll notice in the background that we have our typical 2D layout of our project grid. Well, this allows us to do a 3D project grid. Down here at the bottom, you'll notice some different options that we have. For example, Cartesian, which is maybe more of a square, rectangular, 3D drawing grid. But we also have spherical, cylindrical, and incline. So this really plays an important factor, again, for these not so simple geometries that you may have, but you have different snap points in a 3D type environment that you'd like to utilize. Well, that's where these line grids may come in handy. Under the grid snap settings, well, this is my current grid that I'm viewing here. Default when you do launch a program is this rectangular grid, but we can change this to polar if we'd like, if we're working with a circular type structure. And right now for Cartesian, I have 50 feet on either side of my origin, but I can also check this checkbox so that the project grid will actually grow with the structure, so it'll move dynamically according to the size of the model. Or if I shrink my structure down, that project grid will shrink down too, so I'm not always having to go back in here and change my settings to something bigger or smaller. For now, we'll just leave everything the way that it is, and we can begin with our first column. So the first thing I'll do is to go up to a new single member. Now, the member type is available in this drop-down here. The member type beam is anything that's just a typical beam or column type element. You'll also notice that we have many other options in here. A rib is something we'll utilize a little bit later on, but we also have tension only, compression only, buckling is something that we'll also utilize in this model today. And then because of our nonlinear capabilities, we can do things like cables or cables on pulleys. We can get into spring elements. So quite a few other options than just your typical application of a beam or a column. But with that said, we will choose the member type beam and we'll create a new cross section. So launching our cross section library, you'll notice that we have our rolled sections where you'll find all of the sections from the CSA code, the AISC code, maybe aluminum sections from the ADM. These are all available in our cross section library. But we also have these parametric thin-walled sections. We have massive sections for concrete. So you'll notice maybe in some other software you're really left with only a rectangular, circular type application for cross section. But here we can utilize things like I sections, T sections, same with timber sections here. And we can even get into built-up type members. So we're not limited to just those sections directly from the codes, but we can really utilize a wide array of cross-sections here. For example, if I have an odd thin-walled cross-section here, all I need to do is to define my geometry, and then the program will automatically calculate the section properties for me. We also have two standalone programs called Shape Thin and Shape Massive, and this is where you can import in a DXF file, for example, and that will calculate the section properties for you, and then we can import them directly into RFEM. Those are our standalone programs. For today, we will go with a typical I section, and here is where we can use our filters on the left-hand side. From the first drop-down, you'll see that we have many different standards here. So that's great. If you do a lot of international projects, you'll have access to all these as well in RFEM. This is independent of any add-on modules. Today, we'll be working with the AISC, and we want to first choose our W shape. Now, we have this long list of W shapes, which just comes directly from the AISC 2014. But perhaps you use a lot of the same sections and you don't really want to scroll through this long list every time to choose your specific W shape. Well, this is where we can utilize our favorites group. And with a favorites group, and I choose my edit button here, I can simply check on or check off maybe a set of sections that I use quite often. Then when I click OK and I activate this favorites group, then I'll have these sections available from a quicker list than having to sift through everything. For today's example, I added a couple W shapes that I know I'm going to be using for this example. So now I have quick access to them. We can also set the material in the same dialog box. You'll notice in this drop-down menu, the default when you open up RFEM is concrete F''C 4000, and we have steel A992. So for right now, we'll just utilize the default material in the program, but later on we'll have to add in some more materials to that. The member hinge is set at fully fixed. So right now we will not add in any member hinge, but later on we will do this as well. So now I'm ready to draw my first member. Well, typically when drawing the member, we need to change maybe our drawing grid and maybe snap to a couple different points. But another useful feature with this dialog box when I'm drawing a new member is to simply specify the length and the direction. So I can set the length to 12 feet here, and I want to draw it perpendicular to my work plane. So my work plane is set in the global YX axis. All I need to do is just to click on a couple points here to draw in my first columns. And now you'll notice that the orientation is in the correct direction and my length is set correctly too with that useful feature. The next thing to do is to draw a beam member connecting our two columns. So again, I'm just going to go to my Draw New Beam. I'm going to create a new cross-section. And once again, choosing a rolled cross-section under my favorites list, I'm going to choose a W12 by 40. And I just noticed I used a W12 by 40 here. That's okay. I wanted to actually use, which I can click on this Edit Cross-Section, and we can edit it here to quickly change that 12 by 40 to a 10 by 33. That's my column member. So now you'll notice that my columns are 10 by 33 that I've already modeled in here. And then my new member will be a W12 by 40. I want full fixity, so still no member end releases. And now I can snap to the top of those columns. And you'll see those green snap points pop up. That's just related to those snap features that I showed you when we first opened up the program. So I want to create a couple copies of these. So rather than utilize the Move Copy tool, if I just highlight everything here, I hold down my Control key, then we can utilize the drag and drop feature. So we can quickly create copies of this member, additional couple stories here with just holding down the Control key, drag and dropping, and the program will do that automatically for us. Now the next thing I'd like to do is to select all of these members, and I want to right click under the member option. I will create nodes on lines and intermediate nodes. So here I'm going to add two intermediate nodes, and you'll see that this member is still a single continuous member, and these nodes, if I double click, are of the type online. You can see here we have either standard or online, so the program knows to integrate that directly into that member. So now that we've added those nodes, I'm going to select everything above my bottom two nodes, and I'm going to utilize the Move and Copy tool here. I'm going to create two copies in the global Y direction of 16 feet. And we have a special feature down at the bottom of this dialog box called Edit Expanded Settings. So when I open up this additional dialog box, we can actually create lines in between our copy nodes. And even more so, we can assign a member cross-section to those lines. Every cross-section or every member is composed of a line underneath it. So because we're creating members between these copy nodes, maybe I want to choose a cross-section from my Edit Member dialog box here. Well, I've already defined the W12 by 40 previously, so now that's available in my drop-down box here. I can click OK through all these dialog boxes, and now you'll notice that the program automatically created these beam elements between my copy nodes, so I don't have to sit there and to draw in all of those additional beams, but rather to utilize that function. So now I'm going to select this rear portion of my steel frame, and holding down my control key again, I'm going to make an additional copy right adjacent to it. And you'll notice that when I made that copy, I technically created a column on top of this column, but the program's smart enough to merge those together so we don't have any issues with duplicate members being on top of each other. So again, a nice feature of the drag and drop. So essentially, we have the basic structure for our steel structure here. Now, the next thing that maybe we'd like to do is to put this into elevation view, and I'm going to hold down my control key to select all of my intermediate beams here. And you'll notice that they are highlighted with red, and what I can do is to right-click under Member and choose Edit. Now, under the Member Hinge, this is where I'm going to create a new member hinge. Up pops our member hinge dialog box. We have a nice picture here showing us exactly what our local axes are. So there never is any question, okay, well, I'm not quite sure which axis I'm releasing in terms of translation or rotation, because this picture shows us exactly how we're applying that. So we have the usual release or fixed application for translation or rotation over here on the left. But we can also apply partial fixity, which is very common for a lot of connections. Maybe we don't have a fully fixed or fully released connection, so we can apply that spring stiffness here for partial fixity. And then again, because of the nonlinear capabilities within the program, if we want to apply a nonlinearity to this particular end release, we can. Things like slotted connections, for example. We can include partial activity, which if I go into this dialog box, this details dialog box, we can create some type of relationship manually here between the rotation and my moment. So again, very technical if we want to get in terms of the more advanced features of modeling here, or we just leave this as none and we can apply a simple moment release to the ends of our members. So now for any member that I model in the future, I'll have this simple moment release to apply from my drop-down box here. You can see that the program applies a little pinned symbol here at the ends of my members, telling me that I do have a moment release at that location. So the next thing to do is to maybe add in a little bit of lateral bracing here. For this, I can once again create a new member. I'm going to go to my cross-section database. I'm going to choose an angle. And here, if I deactivate my favorites group, we have all of the AISC sections, whether that's the same measurement for both of the legs here, or we have different lengths for our legs. Activating my favorites group, I've already added this L5x5 that I'd like to utilize within this application. So now Steel A992 is not applicable, so I can quickly create a new material. Now, this material database looks something similar to our cross-section database. We have the filters over here on our left, and we have all of the materials from the AISC 360. But I can also activate my favorites group here, and you'll notice that I have just a handful of materials that I use quite often for my modeling. Steel A36 is what I'd like to select here. I click OK, click OK. Now the member type, I'm going to set this as buckling. So what does this mean? Well, this means that when this member exceeds the Euler buckling load, the member will actually be taken out of the analysis and the iterations will be reran. This is to make sure that if a member fails, our structure is still stable. So we'll set this to buckling. You'll notice that the member hinges is automatically grayed out. This is because we assume that you would like to have a full moment release for any type of tension only, buckling only, compression only member. We click OK, and now we can zoom in here and we can snap to our corner points where we'd like to add in this bracing. So once I have these two braces modeled, I can use my selection tool and utilize that drag and drop feature to add some additional bracing to the structure. And basically, looks like we have some mistakes here. No problem, I can delete that. And we will draw in an additional L member here. And all I did was just not snap to the correct place, but you can see how quickly it is just to select your member and to delete it and to recreate this, which we can just use the drag and drop feature once more, and that looks a little bit better. So now that we're done with our steel structure, what I'd like to do is to maybe create a adjacent concrete structure, and we'll connect those two structures once we're done with our concrete application. Utilizing this tool here to set the origin of the grid or work plane. All I need to do is to select this tool, and then I can click on the corner of my structure at the first level, and you'll notice that my drawing grid has now been placed up to my first level. So it's nice that we don't have to go into a separate dialog box to rearrange the origin of the drawing grid, but we can do so just at the click of a button. I'll once again turn this into elevation view. And what I'd like to do now is to add some nodes to my structure. What I could do is to utilize this feature, add a new node, and draw it graphically. Or we can use our tables down here. So to utilize the tables, you'll notice that I'm under table 1.1 nodes. I'm just going to scroll down to a place where I have some open space. I'm going to create my first node, and all I need to do is to specify the specific coordinates that I'd like to apply this node. So we'll start with -23 in the x, -25 in the y, and z will be 12. And then simply using my down arrow, I'll create my second node at 39, -3, 12, and lastly, my third option will be at 15, -45, and 12. So just another way that I can create these nodes, as you can see them up here in my graphics view, quickly rather than utilizing the drawing feature up here. So you're probably wondering why I'm creating these odd looking nodes kind of generated out here in space. Well, the next thing I'd like to do is to create my surface element. And the surface element is going to be my elevated concrete slab at this first level. So utilizing this drop-down box up here in my toolbar, you'll see all of the different surface applications that we have. And what's nice is that it's not just a typical rectangular section, but things like parallelograms, circles, semicircles, ellipses, polygons. Basically, any shape that you can think of is probably applicable here within the software, because we really want to cater to outside the simple box when we get into things like odd geometries. But for our case today, we will stick with the typical rectangular shape. And for a surface element, the first thing that it asks me is what material and thickness do you want to use? Well, 4000 psi is default within the program, but by using my edit material button here and to opening up my database, I'd rather choose F'C 5000. I click OK. So now you'll notice that my material has been updated. My thickness, I would like to use 10 inches here. And the stiffness is set to standard. For concrete, for example, this would be a two-way slab, just a standard thickness and stiffness in both orientations. But we also have orthotropic here. And when I click on the details button of orthotropic, Well, this gives me a lot more options within my concrete surface element. For example, effective thickness. If I go to my effective thickness tab, I can specify two different thicknesses in both my X and Y direction for maybe a one-way slab, for example. Then I can even view my stiffness matrix for that particular surface to really see exactly what's going on in terms of the stiffness for each element. We also have a few other options here, such as hollow core slab. We can simply define some of the geometric properties here, and the program will automatically determine that stiffness matrix for us. Grillage would be something like a waffle slab for a foundation maybe, and we have box floor girders here as well. For today, we will just cancel out of this and choose the standard stiffness for a two-way slab. I click OK. So the reason I was utilizing these nodes is because I only need 2 snap points here to create my surface element. Now, I currently have 2 separate elements here. Maybe I'd like one continuous surface for my elevated slab. Well, no problem. If I click on the surface, click Delete, then I'm left with all of the external lines. I can delete this middle line. So now I can go to create my surface, but this time I'm going to select my surface using boundary lines. Again, this same dialog box is brought up, but remembers my settings from last time. I click OK, and all I do is click on those external lines to create my one continuous surface here. Now putting this back into elevation view, we probably would like to add some columns here to support our surface. So what I'm going to do is I'm going to add some nodes, and first I'm going to change this into wireframe. It's a little bit easier to see. So all I'm doing is just clicking graphically now, rather than we added them to the table previously, of where I would like to apply some column elements. And I'm just adding them about 3 feet away from the edges here. And you'll notice that over on the right-hand side, I'm going to skip the application to add a column over here, and you'll see in just a minute why. Now, these are just simple nodes, nothing too special here. So how do we quickly create some columns from these nodes? Well, I'm going to use my selection box, hold down my control key to add or to highlight all of these nodes, and then I'm going to utilize my Move Copy tool again. This time I'm going to create one copy in the global Z direction of -12. And I also want to utilize this create members between my copy nodes, but I'd like to create a new cross-section. So here's where I go back into my cross-section library, and I'm going to utilize a parametric massive section. So here is where we specify our basic geometry of 15 inches by 15 inches. I can click my info button to get all of my section properties here that the program automatically calculates. Concrete F prime C 5000 is good. I'd like full fixity here. I click OK, and I click OK through all these dialog boxes. Now turning this back into the rendered version, you'll see that my columns were automatically created using that Move and Copy tool. So the next thing I'd like to do is to maybe create a second floor. Well, I can hold down my control key, use my drag and drop feature once again, and now I have my second floor here. The reason that I skipped the column over on this side is because maybe I'd like to create a rib type beam underneath my slab here. Well, the first thing I'm going to do is to draw a line element. Now, a line element is not a member. We can create a member from a line element, but it's just a simple line. So here I'm going to snap from the top of my column and also on my first level here. Now, what do I want to do with these lines? Well, if I hold down the control key and select both of them, I can right-click to edit the line. And like I mentioned, this is just another way to create a member, but every line or every member is created from a line. So we have a member tab here where I can select the option available, and I will create a new member type, but this time it will be type rib. Now I need to go into my detail settings here, and the first thing that the program's asking me for is where is the alignment of this rib member in comparison to the surface element? Well, I'd like to move it onto the local positive Z side of the surface, which you can see my little picture updates here. And we can actually take into account for both the analysis and design portion of this rib some effective widths. We can either do this automatically with L/6 or L/8, or we can manually enter them in. So for side 1, I'd like to choose L/8, which will be this side over here. For side 2, I'm going to choose manually 3 feet, and that's because I'm at the edge of my slab element here. I click OK. No member hinges will be applied here. And what I do want to do is to create a new cross-section quickly with my parametric massive shapes. And this time it will be a 15 by 22 inch deep member. Click OK. And now you can see that that beam member was dropped down below the surface, but it will be taken into account with the effective width of the surface itself. Now, all the program's doing is dropping little rigid links along the length of the member at every finite element for the surface. Okay, so one other thing we need to do before loading our structure is we need to quickly apply some nodal support. So I have a quick button here to apply a new nodal support, but I can also utilize my project navigator here. You'll notice here's my cross sections within the program. Here's my surfaces. Here's my material. So all of your input data is available here as well. So under the option Nodal Supports, I'm going to right-click and choose New Nodal Support. Again, this should look similar to the member end releases that we utilized before. We can either set this as fully free or fully fixed in terms of translation and rotation. We can also do partial fixity. And then the nonlinearity of the capabilities of the program will allow us to take into account things like partial activity. Maybe we have a sliding or we have friction that we'd like to take into account. All of that can be done. For us, we will just choose a fully rigid connection, and then I can choose the bottom of my structure and the nodes graphically, click OK. I'll turn off my grid settings down here at the bottom, and now I have my structure with the nodal supports applied. One other thing we'd like to do is to quickly connect our two structures here. We have the member type, we'll choose beam here, and selecting a W12 by 40. The member start, I would like it to be fully fixed, but the member end, I want to apply that moment release. I click OK, and then you'll notice that I have those snap points, and automatically the program recognizes what is perpendicular to the surface here. So I don't even necessarily have to create a new node, but I can utilize those snap points. Okay, so the next thing that we'd like to do now that we've automatically created the generation of our structure is to apply some loads. So up here under new load case, we can create our first load case and give it a description of dead load. Now the action category is important because this tells the program how to apply it to the different load combinations according to the ASCE 7. You'll notice that for dead load, self-weight is automatically checked on. So this is how we can take into account the self-weight of the structure automatically based on the element's densities. We create our second load case. This one we will call it live and give it an action category of live here. You'll notice self-weight is checked off, otherwise we'd be accounting for it twice. And lastly, we will create a third called wind and apply it to the action category of wind. Under combination expressions here, the program is going to create both LRFD and ASD combinations. I can click this little info button if I'm curious to see exactly what combinations are applicable from section 2.3 of the ASCE 7. Under load combinations, this is where my load combinations will actually be generated for both LRFD and ASD. But what's nice is you'll notice that only the applicable load cases are applied here. So we're not having to worry about sifting through snow loads or earthquake loads, and we haven't applied them to our structure under the load cases tab. So we only have dead load, live load, and wind load available here. Calculation parameters, this is where we control the method of analysis. We can run this according to geometrically linear analysis. Default in the program is a second order analysis where we can take into account both big P delta and little p delta. This is requirements of the standards. AISC, for example, requires this as well as ACI. So this is default within the program, but we can always change it here. Result combination is nothing more than an envelope solution for all of our LRFD combinations and ASD combinations that was created automatically. So now that we have our load combinations generated, I'm going to use my drop-down box up here to make sure I'm under dead load. So now any loads that I apply on the model will be under that load category. The first thing to do is to apply a new surface load. And under surface load, you'll notice that we have the load type force, of course, what we'd expect, but we also have things like temperatures and axial strains, even rotary motions. Then you need to specify the load direction. We will stick with the global ZL direction. You'll notice as I switch through these different options here, my little picture updates to show me exactly how I'm applying this load to the structure. We will apply a magnitude of negative 0.1 kips per square foot. I click OK. All I have to do is to click on those single surface elements to apply that dead load to my elevated slabs. In a similar manner, we would like to apply a dead load to our member elements here, and we could certainly apply a single member load in kips per foot on each one of these, but rather I'd have the program maybe determine what the tributary areas are for each member and do that automatically, which we do have a feature for that. So under Tools, Generate Loads, you'll see here that we do have snow loads and wind loads, for example, according to the different standards such as ASCE 7. But with that said, these snow load and wind load generators require a structure that looks similar in geometry to this. When you get outside of this realm, you can no longer use the generation of these load combinations for the application of the structure. But if you do have a structure similar to this, this is great because then we can choose a place on the map here, for example, that we'd like to apply our ground snow load, give it a few other factors, and the program can automatically create that for us. For today, as I mentioned, we don't have a structure. We have a little bit more odd geometry. So under Tools, Generate Loads, we'll choose this option from Area Loads via a member. Now, similar to what we saw with the surface load, we needed to give it the area load direction, and the global ZL direction is what we'll choose. And the magnitude will be negative 0.1 kips per square foot. What I'd like to do now is to choose my corner nodes. So what I'm going to do is I'm just going to choose my corner nodes where I'd like to apply this area load. And there's a couple nice features about this. Number one is that it doesn't have to be a typical rectangular application, but you'll notice that I'm actually choosing a polyline application for an odd geometry, for example. And number two is that I'm applying it to different levels here and to closing off each plane individually. So I can apply this to not only my first level, but also the second and third at the same time. So all the red members are highlighted, which this area load will be applied. But now I can exclude members parallel to a certain member. So I can graphically choose, let's say, for example, this member here. I click OK. The program will automatically create this area load, which we can see by this faint gray line here. And maybe I'm interested to see how this load was applied to each member. Well, I can right-click, display separately, to see that I'm only applying it to these members in the global Y direction, and I can view the magnitude by zooming in here as well. So just a quick application so the program can automatically figure out these tributary areas. In the same sense, I'm going to apply a live load, again with a surface load. And all I'm going to do is to change the magnitude to negative 0.05 kips per square foot, click on my two surfaces. Under Tools, Generate Loads from Area Loads via Member, the program remembers all of my settings that I just previously set for my dead load. So all I have to do here is to select negative 0.05 to change my magnitude. I click OK, and all of those loads are automatically generated for me. I can right-click to display in a little bit of a nicer view here if I'd like. Lastly, we want to apply some lateral loads here according to wind loads. The first thing I'm going to do is choose a new line load. A line load is different than a member load, which is right next to it, because a line load would be applied to a surface element here where we don't have a member at this location, but rather we have a line element. Again, this should look familiar to what we've seen, maybe a little bit different view, but all we're doing is applying a load direction in the global Y direction this time and giving it a magnitude of 0.3 kips per foot. Then all I have to do is just to click on these different line elements to apply that lateral load. Maybe for my members up here, I'd like to apply a member load though. So right next to line load, I choose member load. And again, a few more options here in terms of temperatures and axial strains. For this, we'll stick with the global Y direction and apply this as 0.3 kips per foot. I click OK, and I click on this single member. So lastly, for our wind load, we probably would like to apply member loads in a similar fashion to these vertical columns as well as our steel structure and our concrete structure. Going back to member load, this is where we can utilize maybe the trapezoidal function. And you'll notice here that we have the tapered option. We can even get into parabolic type load application. And in most of our loads that we manually apply, we have this bearing option. And if I go into the details of this, you'll notice I can import directly from Excel multiple locations along my X length of my member as well as the load magnitude. So just for more complex applications, for today we'll stick with this trapezoidal load. P1 will be 0.1 kips per foot, P2 will be 0.3, and I'd like it over the full length of the member. So now I can just click on my members here. Now you'll notice as I'm clicking on these members that typically with wind loads, I would like to apply a higher magnitude at the top and lower magnitude at the bottom. Well, that's fine for over here, but it looks like our concrete members are opposite. So I could easily double click on these member loads and switch them around, but you'll notice that my columns start by the big red arrow here at the top and finish down at the bottom, whereas my steel are opposite of this. So maybe I'd like them in the same orientation. Well, for this, I can highlight all of my columns. I can right click and I can choose under member here to reverse the member orientation, and now my loads look more similar to my steel. So that's just another option you have if you want to quickly reverse the I and J ends of your members. Now with that said, you can see that all of our different load combinations with the correct load factors will be applied graphically here as we scroll through the different applications. And now I'm ready to run an analysis. The first thing I want to point out when we run an analysis is under Calculate FE Mesh Settings, the global mesh settings are set at 1 foot. I think that this is fine for maybe an elevated slab, but you can always change these to something smaller as well. Now we do have FE mesh refinements that you can create about a particular node or line within the element. It's a little bit more advanced feature that we won't get into today. But if I go to Calculate, Generate FE Mesh, and I turn this into wireframe view, you'll notice that everything was automatically created for me. I never have to worry about tying these nodes into elements, making sure that my FE mesh is submeshed further. The program does all this automatically. If I were to make any changes within the model, move these columns around, everything will be updated accordingly. Okay, so we're now ready to run an analysis, and I can simply go to Calculate, Calculate All. So now the program is running through all of my different load cases, load combinations, and result combinations. It is doing a nonlinear analysis, and the reason why is because we want to take into account both big P delta and P little delta. We also get a little diagram here showing us our iterations versus our max displacement. If you notice that this is starting to just increase and increase and increase, then we probably have some type of instability within the program. After the analysis is run, then the program automatically jumps to our results tab available in our project navigator. So here is where we can graphically view all of our different deformations, for example, in the different translation and rotation directions. Under the display tab and under the results tree here is where we control everything that we're viewing graphically here for our results. So you can feel free to change this around if you'd like, if you don't like the look of some of it. Back under the results tab, we also have the options to view members. For example, maybe I want to take a look at this column line here and I can create a specific visibility. Well, when I'm looking at my members tree, well, I can activate maybe my axial loads within my columns I'm interested in. We can take a look at moments here, shear forces, everything that's of interest probably for our design purposes. I can always right-click on any one of these and choose results diagram. And when I choose results diagram, I can turn on those same diagrams, but this will just give me a little bit more of a useful look at the magnitudes along the length of my members for my internal forces. We can also scroll between the different load combinations here, and we can even change members with this drop-down box. And lastly, we have our surfaces available. If I cancel out this visibility mode, and I zoom out, let me turn off my members. Well, for our internal forces here, these are important for concrete design purposes. We give these to you in terms of contours. We also have section cuts, but again, I won't get into the details of that. But we can view our surfaces here, such as MX, MY, MXY, that are important when we're looking at reinforcement design of the surface. So with that said, that really everything that we've done up until now has been in RFEM alone. So this is the analysis portion. And I want to make the clear distinction that I want to jump into one of the add-on modules. So back under the data tab, now I'm deciding, okay, now that I have all my internal forces, I'd really like to take a look at design per the AISC. So I'm going to launch my add-on module, STEEL AISC. And you'll notice the add-on module is nothing more than a simple dialog box within RFEM. So all of my materials, my cross sections, my geometries, my member lengths are all brought into this add-on module, including our load combinations here. All I'm doing is specifying a little bit more information related to that specific standard to do my code check. So the first thing I do is I'm going to use my drop-down to select LRFD 2010. My ultimate limit state design, maybe I'd like to select all of my LRFD load combinations, serviceability, I can select my ASD load combinations. My members I select graphically for design, which I can do so here by selecting all of my vertical column members. And maybe I'm not so interested in these braces, so I'd like to exclude them from my analysis for now. And then I just simply work down my list here. Going down to materials, steel A992 was brought into the add-on module. Cross sections, same thing, my W10 by 33 is available. Intermediate lateral restraints, this is just if we have any top or bottom flange bracing along our member length, we could specify that here. Design parameters, effective lengths is going to be buckling about our strong or weak axis with our unbraced member lengths, which default to the full member length. We also have torsional buckling and lateral torsional buckling that we can take into account. Design parameters, just a few more variables that are in regards to the AISC 360, such as the C sub B factor. Again, most of the stuff you maybe just leave at default and what the program calculates for you. Lastly, serviceability data. We can check deflections according to a specific deflection ratio. Under my details tab is where I have my limiting deflection set at L over 360 for simply supported members and L over 180 for cantilever members. I can adjust this equation or this ratio if necessary. And here, all I do is again select my members, and I'm going to select all of my columns graphically. And we'll have to exclude the braces because I did select them within my selection box, but I don't want to check the serviceability for them right now. And the full member length is default here for the reference length. I can add in a pre-camber if I'd like to. And then I'm ready to run my calculation. You'll see that this solves within a split second, and that's because the internal forces have already been solved for within RFEM. All it's doing is taking those internal forces into this add-on module and applying the code checks to those specific members. So our results are available here, designed by load case, designed by cross-section. We can even view the design by member. What's nice is that as I scroll through this table here in my add-on module, you'll notice that I'm synced up to the graphics view within RFEM. Even this big red arrow tells me exactly where my internal forces that are controlling for this specific code check are. One very powerful feature, which I always point out almost every webinar, because I think that this is a little bit more unique to our program, is that we don't just give you our controlling code check here with our big green smiley face because we are under 1.0, but we give you the code check that is applicable throughout the entire AISC for that specific member. So you'll see Chapter E, Chapter F, Chapter G, all of those checks will be given to you here. And even more so, we give you all of the variables that go into play for this, as well as the variable references directly to the code. So again, just very powerful in us trying to be as transparent to you as possible where your numbers are coming from. We can also view everything graphically here, and when we're in the AISC module, which you can see here from our drop-down list, RF-STEEL AISC, we can view either the ultimate or serviceability cases graphically if we choose to do so. So that's really all I wanted to show you in terms of the steel design. Again, I know I flew through this. I did a complete 1-hour webinar devoted to only steel design and this add-on module that if you'd like to see that in much more detail, I want to reference you again to our YouTube channel. In a similar sense, I want to launch our RF concrete members to just show you real quick maybe what concrete member design would look like. You'll notice that the add-on module looks pretty familiar. That's the great thing about our program is a lot of these add-on modules look very similar. So once you learn one, all of the rest of them are pretty intuitive to understand how to work through them. The first thing we do is to select our standard ACI 318 from our drop-down. Strength limit state, I'll select my LRFD load combinations. My serviceability limit state, I will select my ASD load combinations. And then again, I just move slowly down my list here. Materials, F'(C) 5000 is applicable. You'll notice these steel are red. That's because they cannot be applied in a concrete design add-on module. That makes sense, no problem. Cross sections, same thing. The only ones that are applicable are going to be our rectangular concrete sections here. The program is smart enough to recognize that we have some rib members, and it will take into account the effective widths when we're looking at design purposes, which we'll see in just a moment. Then under reinforcement tab, this is where we specify the different longitudinal and shear reinforcement factors. For example, the first thing that we want to do, you'll notice that all members are being designed. Well, we have a lovely steel section pulled up in our concrete add-on module. This is going to probably give us an error if we try and design that. So instead, I'm going to graphically choose just my 2 rib members here. I click OK, and now here's our rib members shown in our little preview box here. So working from left to right, I want to choose my longitudinal reinforcement. Maybe I'd like number 8s and number 9s. I can choose maybe 2 layers for my longitudinal reinforcement if that's needed. The anchorage type, we can change this to straight or hook. Bend, you'll notice again the picture updates here according to whatever selection we choose. Ties and stirrups, same concept. Maybe I'd like to choose number 4s. We can also control the spacing of the shear reinforcement down here at the bottom. The reinforcement layout is just cover spacings, which the little picture here will update to show you exactly what variable you're setting within this entry over here on the left for our cover. The reinforcement layout, we have some different options, whether we want an optimized distribution or maybe we want to set a ratio of our top reinforcement versus our bottom reinforcement. Now, an important thing to know is that this is the design internal forces. So right now we have everything checked. So the reinforcement will be designed for axial forces, shear forces, moments, as well as torsion. We can always uncheck one of these if we don't want to take them into account. Minimum reinforcement, if we'd like to put in a minimum reinforcement for area, we can do so here. Otherwise, when we have these 2 checkboxes checked, the program will refer to the ACI standard and put in the minimum reinforcement that the standard calls for. The ACI 318 tab, just a few more parameters according to the ACI, such as percentages of reinforcement. The default is set at 8% here. Shear and torsion reinforcement will refer to table 22551. And then, of course, if anyone has ever done concrete design, we're all familiar with these strength reduction factors according to Chapter 21 here for compression, tension, shear, and torsion. So these come directly from the code, so chances are you won't be adjusting these. Lastly, serviceability. With serviceability, we can design for crack width consideration. Crack width is not within the code, but rather with this first checkbox here, it's saying design without direct crack width consideration, but rather according to Chapter 24, which is spacing of our reinforcement to control our serviceability. And realistically, this is related to cracking, but it's more so a requirement of the code to not directly measure the cracking itself. Now we can apply the Gergely and Lutz equation to come up with a theoretical equation to calculate the crack width within the member and compare it to some limiting values here. If we want to do so, we have some suggestions here from the ACI committee. Maybe we will choose 0.02 because our structure is in a very dry environment. So now we'll check according to both crack width and spacing requirements for serviceability. We can also take into deflection and more so to activate the long-term deflection with a specific factor according to 24241 within the code. So now we're ready to run our calculation. Again, all of those internal forces are already solved for in RFEM, so you'll see rather quickly that we get our results for our two rib members. We have our results section here, of course required reinforcement, and this is just based on the internal forces. You'll notice a few additional notes here. We can always click on messages to see those code references of exactly what these little notes within the program are trying to tell us. Then we'll get provided reinforcement. This is nice because obviously required reinforcement is okay. This is just an arbitrary number, but we'd like to see the applicable bars within the design to see how we're going to meet those required reinforcement. So we have both longitudinal reinforcement. We can see our shear reinforcement here. Now we have pretty close, tight spacing here of our shear. That's probably because some torsion effects, which we could always go back and choose to uncheck that for our internal force design. Now, if I choose 3D rendering here, this will just give me a nicer view of my reinforcement throughout the member. Maybe I'm not happy with one of these. Well, I can always double click on one of these reinforcement settings and adjust my bars here, including the location of the spacings along the bar length. So very, very powerful when it comes to our reinforcement for concrete. Okay, so exiting out of this 3D view, we also have our serviceability check. This is more so in table format. Looks like we're a little bit overstressed, or not overstressed, but our limiting crack or spacing for our torsional reinforcement is exceeding the capacity here. Well, this is a good example here of a live webinar. It was passing before, but it looks like now we aren't passing, so maybe we'd want to go back and address some of the spacings for our longitudinal and shear reinforcement to meet those code standards. But again, this will just show you when you aren't passing and how to better change around the input data to meet that. So for now, we'll forego this and jump into our graphics view, which I just lastly want to show you that, again, we're still within this RF concrete members here. And this means we're still looking at the add-on module. We're just viewing graphically some of our results. So here's where our required reinforcement is. And you'll notice that maybe I could create a little section view of my two members here that I designed for. And I have my AS top required, my AS bottom required. Now maybe I want to compare that to my provided reinforcement. So for example, I can turn on my AS bottom, which is this nice diagram here given in inches squared per foot. And I'd like to see how my provided meets the required. Well, you can see that it looks like we're well over the required reinforcement ratio here. So you can view everything graphically. What's also nice is that if we turn off these diagrams, we can also view a rendered shape here of the reinforcement within this particular model with even the rib section. So we can always add this to our printout report if we see this as fit. So again, breezing through this add-on module, I have an entire previous webinar that I dedicated to only column and beam design for reinforcement. I also did another webinar that was strictly for surface design, reinforcement design according to the ACI, which I would encourage everyone to take a look at if you're more interested in those capabilities. So the last thing to just show you before I sum up this webinar is our printout report rather quickly. Up here at the top, we can view our printout report. And the program's now cycling through to create that printout report. And what it's going to do is it's going to open up this completely separate application. I think that our printout report is very, very powerful. You'll notice that we have our table of contents, which looks very similar to our project navigator back in RFEM. As I scroll through these different options here, and maybe I scroll in to view this a little bit closer, well, the program's going to update in my graphical view as I click on my table of contents over here on the left. I think everything is laid out quite nice in terms of the different tables. For example, if we scroll in here to cross sections, for example, you have a nice little picture showing you all of the different cross sections that were utilized within the program. If we take a look at member hinges, we give you a little picture here so that your engineer reviewing these calculations won't have any question about, well, I'm not quite sure which axes they released or which they didn't, but with this picture that will be helpful for those review engineers. We even have our add-on modules located down here on the left, which you can always move around the orientation or the order of these add-on modules if you'd like to do so. And for our concrete members, we also automatically create a nice picture here of our reinforcement, which is a nice touch as well to the RF concrete add-on module. So you can add on your company logo here. Very powerful, like I said, and I think it's laid out quite nicely. Under settings, printout report template, under edit selection, we can always control what we are and what we are not seeing within this add-on module. The last thing to show you is to maybe exit out of this, and of course we always want to add pictures to our add-on module. And just a nice feature to show you is maybe we select this column line and show our visibility by our selected objects here. I can zoom in, and I'm going to jump to one of my load combinations. Here I'm going to display my support reactions, and I'd like to print off this picture, but I'd like to do it for all of my load combinations. Well, we have a nice feature that if I go to this print graphics option up here, we have mass print. Now when I go to the details of my mass print, and you'll see we have 3 different tabs here, but right now the program's suspecting that I'd like to view what's already turned on here, my support reactions, because that's what I'm viewing graphically in RFEM now. Well, I can choose the option to print off all load cases and combinations at once. So what does this do? Well, when I click OK, what the program's going to do is it's going to take this exact view that I'm looking at here, and it's going to cycle through all of the different load cases, load combinations, and result combinations to show me my different support reactions in all of those scenarios. It's going to automatically create those pictures, export them here to our printout report, and now you'll notice I have this little list here in my table of contents of my support reactions. If we zoom in, once this loads, you'll notice that as I scroll down through these, I have load combination 1, load combination 2, 3, and all of those support reactions are automatically generated. So it's also a nice feature that if I go back and I make any changes to this add-on module, or sorry, to RFEM or the add-on modules, basically to the structure in general, that these pictures will be automatically updated, so I don't even have to worry about reprinting them. So again, just another useful feature rather than sitting there and having to print off each individual picture yourself. Now we are ready to sum up the webinar today. Again, I know I flew through a lot of that. I just wanted to give our new users a basic introduction to the program and the add-on modules. We have much more information on our website at dlubal.com on both RFEM and the add-on modules. You heard me reference our YouTube channel quite often, so please feel free to visit there to view previously recorded webinars. Our email here at our Philadelphia office is info-us@dlubal.com, and the phone number is 267-702-2815. Feel free to reach out if you have any further questions or comments about today's webinar or anything else. We do have many more upcoming webinars. As I mentioned, this is just webinar 1 of a 3-part series. Webinar 2 will take place on May 18th. And we also have webinar 3, which is integration into BIM workflow. So just a little bit more advanced features within the program as we're slowly ramping up to more details within the program that we can dive into rather than just the basic introduction. You can register for both of these webinars at dlubal.com under support and learning and webinars. Of course, as most of you know, I try and send out a reminder email, a couple of them before these webinars come up as well. If you are wanting PDH credit for today, that's great. I will be happy to issue that. My request is that you please email me at info-us@dlubal.com. Again, that's info-us@dlubal.com. Please let me know who was in attendance for today's webinar, and I will issue that PDH certificate to you and send you an email back. With that said, that concludes webinar 1 for today. So I want to thank everyone for attending, and I do hope to see you at our second webinar. Thank you and have a great day.